Assalamualaikum warahmatullahi wabarakatuh. My name is Kasma Saharuddin from Malaysia Japan International Institute of Technology, University Technology Malaysia. As the first author, today I will present my article entitled Prediction Model of Magnetorheological Fluid Damper Hysteresis Loop using Extreme Learning Machine Algorithm. So let's move to introduction part. Okay. First of all, I want to explain what is meant by smart material. Smart material is the material that its properties can change by external stimuli, for example, temperature, electric field, and magnetic field. Thus, magnetorheological fluid or MR fluid is one of class of smart material due to its properties which is reversibly and rapidly changed by external magnetic field. As shown in figure 1a, it is a pure MR fluid where there is no applied magnetic field. The condition of MR fluid without magnetic field is like normal liquid, but when in presence of magnetic field, the condition can be seen like shown in figure 1b. The MR fluid will change its state from liquid to semi-solid state. The position for magnetic particle can be illustrated in figure 2a and 2b, where when no applied magnetic field, the particle moves freely without specific direction, and when we apply magnetic field, the magnetic particle will align follow the direction of magnetic field. The advantages of MR fluid are as stated, where it has low power, high shear stress, good temperature stability, and fast time response. Okay, let's move to next slide. The application of MR fluid can be seen on damper when the commercial name is MR fluid damper or MR damper. So here I show some of the application of MR fluid damper or MR damper. It may use in biomedical such as in prosthetic devices as to replace the conventional one. Then it may be implemented in civil engineering applications such as in bridge cable. Besides, it can use in mechanical engineering, for example in vehicle seat suspension. However, in order to equip this material in various applications, it is crucial to develop an appropriate model to observe its performance. This to avoid any harmful and risk situation when implemented in real design. Then we move to next slide. So, many models have been developed to replicate the hysteresis loop of this smart material. Here, I have made a hierarchy of the existing hysteresis model of MR damper. Generally, MR damper model can be categorized into two parts, which is parametric and non-parametric approach. As we know, parametric model involved with mathematical derivation, which engage with spring, dashboard, and hysteresis element in a model circuit. However, this kind of model use higher order differential equation which is inconvenient to implement in real design. In addition, some of the case, the identified model parameter may reach negative value which is unrealistic, while non-parametric model approach is using intelligence-based model. Among non-parametric model, neural network have shown the simplest method to model this hysteresis behavior. Nevertheless, the conventional neural network required longer training time due to its iteration process such as backpropagation learning algorithm. Therefore, this work proposed new modeling technique to replicate hysteresis behavior of MR damper called extreme learning machine. So next we move to next slide. So basically, there are some advantages of using extreme learning machine, or we call it ELM, which is easy to use, faster learning speed, have higher generalization performance, and powerful in pattern recognition. ELM is going through pre-processing to train the data by using reference data. After obtaining the optimized model, user may utilize the model by inserting the related input to predict the hysteresis loop of MR damper. Generally, ELM have three main steps, as stated in the slide, that make this learning algorithm different from the conventional one. The training process for ELM is start by inserting or declare the hidden nodes and activation function. Then the algorithm will randomly assign the input weight and hidden nodes bias. After getting the result, it will calculate the hidden layer output using Morel-Penrose method. Next, it will calculate the output weight, and then it will produce predicted output. Afterward, it will calculate the performance of the model by calculating the error between predicted output and experiment data. And then we move to the next slide. In this slide, I will describe each variable in ELM structure. Before that, as I mentioned just now, at the first step, the activation function needs to be declared to proceed for next step. Activation function plays an important role in producing better performance in ELM algorithm. Thus, I have proposed three different activation functions, which is Sigmoid function, hard limit function, and sine function. So, in this slide, I have shown the meaning for each variable to make the reviewer more understand the ELM structure. In addition, the table provided in this slide summarizes the model parameters used to model the hysteresis loop of MR damper. Here, the training data consists of 80% of modeling data. The current used for training data are 0.1, 0.2, 0.3, and 0.4 ampere, while 0.35 ampere is used as testing data. So basically here, each current consists of thousands points. This slide shows the result of training performances utilizing three different activation functions with 100 hidden nodes for each activation function. The figure in the table have shown that sine function and sigma function have produced very good performance in training process, while for hard limit, the model may still follow the experiment pattern even though it is not excellent as sigmoid and sine function. Besides, a table is provided to represent the modeling performance using two performances index, root mean square error, which is RMSE, and coefficient of determination, which is R square. As stated in the table, the RMSE between sine function and sigma function have only a little difference, but still, sine function have performed better among other activation function. However, to validate this model, and unlearned data need to be used to observe the generalization of the data. Thus, the unlearned current, which is 0.35 ampere, have been used to test the model. The figure in the slide shows the hysteresis loop between force and displacement relationship of MR damper. All of the results have been plotted together with experiment to observe the performance of the model. As the result, hard limit activation function shows the worst performance among others, while sine and sigma function may fit well with experiment data. To check the tangible result, a table has been provided where it consists of training performance and testing performance. As for training performance, it shows that sine function have performed better among others, but in testing performance, sigma function have shown better, followed by sine and hard limit function. Thus, this shows that sigmoid is the best model to predict the hysteresis loop of MR damper. Let us end of this slide. As the conclusion, here I want to mention that MR damper have received good attention from industries due to its intelligent system. Thus, an ELM modeling method have been proposed to model its hysteretic behavior due to its advantages. Furthermore, the activation function used in the ELM algorithm may affect the modeling performance. After go through the modeling process, it shows that the model with sigmoid activation function is the best model to replicate the hysteretic behavior of MR damper. Lastly, I want to conclude that ELM may be able to predict the MR damper without involving complex mathematical derivation, where it can be used for further application. And thank you.